Okay, we are in the process of repeating what we have been doing in this course. We have been going through the UML part. Now let us look at the OCL part. Yeah, as I said, the OCL concepts, main OCL concepts base on concepts that come from the UML class diagram, namely from the data types, from the classes, from the associations. And the OCL core concepts, I would classify them as objects, values, navigation, logic, collections, and collection operations. So let's go through this. I have handled and discussed OCL already. Oh no, I'm in the wrong collection of slides. Here I have to go there. I have handled OCL already in the first collection of slides. I was introducing UML, OCL, and gave an introduction to use. So the last part of these slides, the first part was on UML in these slides, and the last part was already on OCL. Here we are. We have had seen in this first collection of slides 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 slides which discussed OCL. So we have the option of obtaining for a particular class all the objects of the class with all instances. We can check whether in a collection a particular element is included or not included with includes and excludes. We have the option to filter a collection according to particular criteria. So from a collection we select particular objects and we take it into the result, or from a collection we reject particular objects and we retain those which do not satisfy a particular criterion. We can check for the number of elements in a collection. We can check whether the collection is empty or whether the collection is not empty. We have a universal quantification. We have an existential quantification. We have two forms of collect. The basic idea of the collect is you have a collection and you apply to all collection elements a term that sits here in the collect. So here in the example you have a collection of integers, and with each element you do something particular with the element. In this particular example you square the element, and when doing so it can happen that two different elements in the original collection are mapped through this computation here, through this what you're doing with the element. Two different elements are mapped to the same result, and in order to reflect this fact that when you map two different elements to the same element, and you do not want to lose this information that originally there were two elements and now you have also two elements here in the result, but they have the these two elements have the same, look the same, but you want to keep them as different, and that's the reason why the collect results in a bag when you apply the collect to a set. The collect nested is a variation of the collect. So this is the plain collect. The collect nested is a variation where you keep the structure of the result. Okay, the including and the excluding. The including is sort of a constructor where you add an element to a collection. The excluding removes an element from a collection. Yeah, be aware of including and excluding return collections, whereas includes and excludes return Boolean results. Includes and excludes are checks, are tests, returning a Boolean, and including and excluding are operations that return collections. Including and excluding behave insofar or there's one particularity for the excluding, that the excluding on collections where you have the option to have multiple elements, where you have duplicates, the excluding is radical. It removes all elements from the underlying collection. Includes and excludes are generalized to the case that you can have set valued parameters here. We have discussed that. There is option to have in OCL to have let expressions, to build shortcuts, to build variables. There are tuples in OCL. There's a Cartesian product available. And one particular nice thing that we have discussed, a little bit of complicated, when you have an association class. When you have a plain association class, as here, you have company and person, and you have the association class job. In between, job typically will have the salary attribute in order to care for the fact that one person can have different employers, and of course one company, one employer has many employees, so we have star here as multiplicities. And when you have this general case of a plain association class, this results in 6 different ways in building expressions, 6 different ways in navigating. So you can navigate from the person to the company with the role employer. You can navigate from the company to the person with the role employee. You can navigate from the company to the association class with the name of the association class used as a role name, and typically the class will have a first letter with a capital letter, and then you use here as a role name the lowercase letter. So job with capital letter is the association class name, and job with lowercase letter is this is a role name that you can use to navigate from a company to all the job objects that are connected to the company. So IBM.job gives a set of job objects, and analogously from person you can navigate to job with job, and this gives the set of job objects for a particular person object. In contrast, so this navigation to the association class is multi-valued, is set-valued. In contrast to that, the navigation from the association class to the company is single valued, and also, of course, the navigation from the association class to the other participant here. Yeah, that's because the job object. Do we have an example here? Yeah, we see it here in the friendship example. Each friendship connects two profile objects, and from each single friendship link object, you can navigate to the invitee and you can navigate to the inviter. So this will give one profile as an invitee and one profile as an inviter. And this is exactly reflected here in the fact, in the other example here, that you have the one multiplicity when you navigate from job with employer to company and from job with employee to person. So in the class diagram, you write down the star here, but these multiplicities are the multiplicities that you are using when you go from person to company or from company to person. This multiplicity is never written down here. This is in the class diagram. This multiplicity is, I have just used it here in order to make clear that when you navigate from the job to the company or to person, you get one object here and not a collection of objects. So yeah, and the situation in a reflexive association class is still a little bit more complicated, because you need to involve then the role names here in a particular way. I will not go into the details. Yeah, and in OCL you have the dot shortcut. The dot shortcut is basically the motivation for the dot shortcut is basically you are in a particular class, say here the subject class, and now you go through the class diagram by using role names. So from subject you go via profile to profile, and then you go via inviter again to profile, and from posting with posting to poster, and then with commenter to profile, and you go back with subject to again to subject. So the path that I have been describing was subject, profile, profile, inviter, posting, commenter, and then back to subject. And this is, you can write an OCL expression for this. So you have a subject, say horses, and then you say horses dot profile dot inviter dot posting dot commenter dot subject, and that's a valid OCL expression. And that's the main reason to formally introduce here this dot shortcut. And you see these dot shortcut, several examples of the dot shortcut, and we have been discussing this in detail, in good detail when we have done this material in the first round. Okay, and here you see how OCL is applied. You of course have the option to build invariants with OCL. You have the option to build query operations. You have the option to build derived attributes, and these are just a few options where you can apply OCL in a class diagram. Yeah, that was the part on OCL in the slides when we were discussing the social network example. We have had a closer look on OCL in connection with the collection concepts and the collection operations. In particular, we have several examples again where collections occur, and in particular both examples, this slide and this slide, the main motivation for these two slides are the different collection kinds, sets, bags, sequences, and ordered sets are needed for modeling different situations in an application. So 4 different collection kinds are nice because different situations in the world to be modeled need different collection kinds. The 4 different collection kinds are also needed from a more conceptual perspective, because the 4 collection kinds, set, bag, ordered set, and sequence, they naturally arise when you take 2 criteria and you combine these criteria. 2 criteria in order to distinguish between collections: insertion order and insertion frequency. And the criterion is insertion order relevance and insertion frequency relevance. So you ask yourself, or we ask ourselves, is the insertion order relevant for distinguishing collections? And this can be, this informal question can be formulated in form of an OCL expression which formalizes this idea. So is the insertion order relevant? We have a collection, we include E1, we include E2. We take the same collection and now we include the elements in the different order. Here we have first E1 and then E2. And here we take first E2 and then E1. And this is the formalization of this informal question. And now you ask, and if this equality holds, then we call the collection order blind. And if the equality does not hold, is not required to hold, then we call the collection order aware. So order blind are sets and bags, and order aware are ordered sets and sequences. And the second criterion is the insertion frequency relevant for distinguishing collections? Is it relevant whether I include the element 1 time or 2 times or 3 times? Is this relevant or not? And formally, this informal question can be stated again as a rule in OCL, and it's the equation. Here we have required an equation to hold. Here we also require an equation to hold, and we have here a collection, and we include the element E, and we ask ourselves: is this equal to the original collection here? But we know already that in the collection the element E is included already. So we know that the element E is included in the collection, and now we ask ourselves, hey, this second inclusion of E, is this relevant or not? Yeah, if the equality holds, then the insertion frequency is not relevant, and then we call if this equation here holds, if this property holds, then we call the collection frequency blind. Otherwise, we call the collection frequency aware. So frequency blind collections are ordered set, set and ordered set. Yeah, in the ordered set and in the set, it does not matter whether you include the element once or twice or 3 times. The element will appear there only once. And the frequency-aware collections are bags and sequences. So for bags and sequences, it does matter whether you include the element once or twice or 3 times, and so on. So we have these two criteria, order blindness, order awareness, frequency blindness, frequency awareness, and this give these two criteria, the order and the frequency, give a nice distinction here for the collection kinds. And this is a second motivation why these 4 collection kinds should be present. So the first motivation why the 4 collection kinds should be present is we need them. We need the 4 collection kinds to model particular situations in the real world, in the application. And the second motivation for having these 4 collection kinds is the 4 collection kinds naturally come from these 2 very basic criteria. Okay, yeah. These were the considerations on the collection kinds. We have a lot of collection operations. So first there are collection operations which are defined on all collection kinds, and then there are special operations which are only defined on special collection kinds. So I mentioned already first, last, add, and reverse are only defined for order aware collections. Yeah, these 4 operations are defined on sequences and ordered sets. These 4 operations are not defined on sets. You can build subsequences, you can build subordered sets, of course only on sequences on ordered sets, not on bags. The intersection is only defined for order blind collections. The intersection is defined for sets and bags. It does not make much sense to define an intersection between 2 sequences. What should that be? And we have on numerical collections, on collections of integers, we have the particular operations sum, min, and max. And yeah, these are the operations that are defined on special collections. More important are the collection operations that are defined on all collection kinds, and you should have these 6 different categories of collection operations. So in total, I do not know, I think there are 30 or 40 collection operations, and there is some, it's better to have some structure there on this 30-40 collection operations. The categories are the constructors and the destructors. Constructors and destructors are operations which build up collections or destroy collections. Then there is a group of 3 categories. There are basic Boolean integer query operations. So these query operations, they return a Boolean result or an integer result. Then there are some advanced Boolean query operations. And the third category are the advanced collection valued query operations. And the 5th category are the complex query operations. So these are really the hard ones. That's the iterate and the closure. And then there are the last category number 6 are the coercions, which just go from one collection kind to the other collection kind, as set, as bag, as sequence, and as ordered set. These 6 categories, when I ask about collection operations, it would be good if you have these six categories in mind when answering this question. You can have in mind here the difference between these three middle ones is the following. The basic Boolean and integer query operations, they are simple insofar they have very easy parameters. The advanced Boolean query operations have complicated parameters here because you take expressions and you take OCL expressions and you use OCL expressions here as parameters. Here you do not, here you see is empty, not empty size does not have any parameters. And here in the advanced Boolean query operations, you use OCL expressions as parameters. So the three dots here have to be substituted by OCL expressions. And the same is true here for the advanced collection valued query operations. These advanced Boolean query operations return a Boolean result, and the advanced collection valued query operations, they introduce a collection valued query result. I will not go into the details. We have discussed examples, nice examples for nearly, for everything. These are the details for the iterate. So it would be nice if you have, this is the general syntax of the iterate. And it would be nice if you have this in mind. If you want to report on the iterate, then you have, it would be nice that you have this here in mind, that the iterate is applied to a collection expression, and the iterate has two variables, namely the element variable and the result variable, and the iterate can have two types, the element type and the result type. And the iterate does have two expressions, namely the init expression and the eta expression. And you should be able to explain how these parts work together. Okay, that was the iterate. The other complex, so the iterate is the one of the complex query operations. The other complex query operation is a closure, and the basic idea behind the closure is, well, to put it in very simple words, the basic idea behind the closure is when you have here a parenthood. The classical example is a parenthood situation where you have a person which has either no parent is recorded, or one parent or two parents are recorded, and a person can have an arbitrary number of children, and you want to specify a cyclicity here of the parenthood relationship. Then you will do it with an expression that uses the closure. So the closure, when you have here a particular object diagram, Ada is the mother of Bob and Sid, and Bob is the father of Dan and Eve. And when you now start with Ada and you consider Ada.children, and you say Ada.children closure child, then you get the children of Ada and the children of Ada and so on. And when you say Ada.child.closure child, then you get Bob, Dan, and Eve. And when you in this object diagram, and when you say the same, when you specify the same expression ada.child closure child, then you get the same, you get the result that ada, that when you're specifying this closure expression, you will have as a result Ada, Bob, Sid, Dan, and Eve. And in this case, then Ada would be included in its own children. So this is an example that this acyclic parenthood invariant fails. And the acyclic parenthood example is satisfied here. So this is the original specification of the invariant for the acyclicity of parenthood. You say for each person P, it should be true that P dot parent closure parent excludes the P. So this is the classical formulation of the for the acyclicity of parenthood over here, and that is where the closure is really needed. Okay, and in connection with the closure, we have also discussed the evaluation browser. I think we have handled the OCL part so far. So no, let's jump to this one. So in the last minutes I've been explaining the basic OCL concepts here. I have been talking about the different collection kinds and the collection properties, which were about insertion order and insertion frequency, and I have been also shortly recapitulating the collection operations, what is missing and what comes in the next part. I will not go in this recapitulation, I will not go into the use part, but I will, in the last part for the recapitulation, I will go into the meta modeling business. Okay.